Hello, everybody. This is the sixth day of our crash course, and we're going to learn multimodal and reinforcement learning. Multimodal learning refers to the process of integrating and analyzing information from multiple types of data or modalities, such as text, images, audio, and video. Unlike unimodal models that focus on a single type of input, multimodal learning enables AI systems to leverage complementary information from different sources, improving performance and robustness. This approach is crucial in applications like autonomous driving, vision plus LiDAR, healthcare, medical images plus patient records, and human-computer interaction, speech plus facial expressions. However, integrating multiple modalities presents challenges such as data alignment, representation learning, and handling missing modalities. Overcoming these challenges requires specialized architectures, including transformers, fusion techniques, and contrastive learning approaches. Humans naturally process multiple modalities simultaneously. For example, when watching a lecture, we use vision, slides, hearing, speech, and sometimes tactile feedback, writing notes. AI systems benefit similarly from multimodal learning by developing richer, more contextualized representations. For example, self-driving cars process visual data from cameras, depth information from LiDAR, and GPS signals for navigation. This integration improves AI generalization, robustness to noise, and ability to generate context-aware responses. Furthermore, multimodal learning is critical in robotics, combining proprioception, vision, and speech, medical AI, combining X-rays and patient history, and entertainment, enhancing AR/VR experiences. However, multimodal AI requires specialized architectures to ensure effective fusion and reasoning across data types. The recent advancements in large-scale multimodal pre-training, few-shot learning, and self-supervised approaches have further expanded the capabilities of multimodal AI systems, making them more flexible and adaptable to diverse applications. Multimodal learning encompasses various data types. Text-based modalities involve natural language understanding, NLU, information retrieval, and text generation. The vision modality includes images and videos widely used in image classification, object detection, and scene understanding. Audio modalities are crucial for speech recognition, ASR, music analysis, and environmental sound detection. Lastly, sensor modalities such as LiDAR in autonomous vehicles, EEG signals in brain-computer interfaces, and depth sensors in AR/VR provide structural and environmental information that enhances AI's perception. Handling these diverse modalities requires methods for representation learning, feature extraction, and modality fusion to build cohesive multimodal systems. Multimodal learning faces several technical challenges. Modality heterogeneity means that text, images, and audio have fundamentally different structures. Text is sequential, images are spatial, and audio is temporal. Learning effective shared representations is a non-trivial problem. Temporal alignment is another challenge, especially in video and speech applications. Ensuring that spoken words align with lip movements is crucial in speech synthesis and deepfake detection. Furthermore, real-world data is often incomplete or noisy, e.g., missing audio in a video call, requiring robust learning methods that can function with missing modalities. Finally, multimodal models require significant computational power, especially when processing high-dimensional modalities like video and sensor data, leading to scalability issues. New approaches, such as efficient token selection and knowledge distillation for multimodal transformers, are being explored to address these challenges. Effective multimodal AI requires learning robust representations that capture relationships between different data types. The three main fusion strategies are early fusion, concatenating raw features, intermediate fusion, processing features separately before merging, and late fusion, combining individual predictions. Additionally, representation learning can be joint, creating a shared space for modalities, or coordinated, separate embeddings mapped to a shared latent space. Contrastive learning, used in models like CLIP, ensures that text and images align semantically by pushing related embeddings closer. Modern multimodal models, such as Flamingo and Byte, 3, utilize large-scale pre-training on aligned datasets, improving cross-modal generalization and robustness. Transformers have reshaped multimodal learning by enabling deep integration across different data types. Vision transformers, VITs, initially developed for image recognition, have been extended into multimodal architectures such as FLAVA, fusion of language and vision, BITE, 3, universal multimodal pre-training, and perceiver, scalable attention across modalities. These models use cross-attention mechanisms to allow different modalities to exchange information dynamically. However, multimodal transformers face significant scalability challenges as processing multiple high-dimensional modalities increases computational costs. Strategies such as mixture of experts, MO, token pruning, and sparse attention help reduce complexity while maintaining performance. Another challenge is modality bias, where one modality dominates model predictions. Research in adaptive attention, retrieval-augmented models, and modality-specific training is improving how multimodal transformers handle diverse inputs efficiently. Multimodal fusion determines how different modalities are integrated. Early fusion merges raw features before processing, allowing joint representation learning but requiring proper data alignment. Late fusion processes each modality independently, merging outputs at the decision level, which improves modularity but can miss deep interactions. Hybrid fusion combines early and late strategies to achieve both modularity and cross-modal interaction. The most advanced method, attention-based fusion, is used in transformer models to dynamically assign weights to each modality. This technique allows models to focus on the most relevant signals, improving interpretability and adaptability across tasks like multimodal dialogue, healthcare diagnostics, and autonomous systems. Self-supervised learning, SSL, enables multimodal AI to learn from unlabeled data by exploiting internal patterns within datasets. Contrastive learning, used in clip and audio clip, aligns different modalities by bringing similar pairs closer in the embedding space. Masked modeling, inspired by BERT and ME, masked autoencoders, trains models to predict missing modality components. Another key approach is cross-modal knowledge distillation, where a stronger, multimodal teacher model transfers knowledge to a smaller, more efficient model. SSL has significantly advanced vision language models, DAL, Flamingo, and audio text applications, Whisper, Wave 2 VEC, by improving robustness and generalization without requiring large-scale labeled datasets. Handling missing modalities is critical for real-world multimodal AI applications. Modality dropout trains models to perform well even when some inputs are absent, improving robustness. Cross-modal imputation predicts missing modality data using learned representations, such as generating speech from text in speech synthesis tasks. Latent space interpolation allows deep models to infer missing features based on available inputs, ensuring seamless cross-modal integration. These techniques are especially valuable in medical AI, where patient data may be incomplete, and speech-driven applications, where audio quality varies. Ongoing research focuses on adaptive models that dynamically adjust to missing or noisy inputs while maintaining strong performance. Evaluating multimodal models requires a combination of general and modality-specific metrics. Accuracy, precision, recall, and F1 score are common for classification tasks. However, each modality has specialized metrics: BLU, Rouge for text, PSNR, SSM for images, and WER, word error rate, for speech. Cross-modal retrieval tasks rely on metrics like recall at K and mean reciprocal rank, MRR, to assess how well models align modalities, such as matching images to text descriptions. For tasks like multimodal generation and dialogue, human evaluation is necessary to assess fluency and coherence. Ensuring fairness and robustness across modalities is an ongoing research challenge. Multimodal models benefit from pre-training on large, diverse datasets before fine-tuning on specific tasks. Joint pre-training optimizes all modalities together, while separate pre-training allows for independent feature extraction before fusion. Datasets like LAON, 5B, How to 100M, and AudioSet provide extensive multimodal corpora. Self-supervised objectives such as masked token prediction, BITE, 3, and contrastive learning, CLIP, improve cross-modal understanding. Transfer learning allows models pre-trained on broad multimodal tasks to be adapted to specialized domains like medical AI or robotics, reducing data requirements and training costs. Healthcare is a key domain for multimodal AI, integrating medical imaging, X-rays, MRIs, electronic health records, EHRs, and patient speech data for diagnosis. Models can detect patterns that single-modality approaches might miss. For example, multimodal AI can assist in disease diagnosis by analyzing both visual scans and patient histories, improving accuracy in areas like cancer detection and neurological disorders. However, challenges include data privacy, regulatory constraints, and modality imbalance, text-heavy versus image-heavy records. Addressing these issues requires specialized architectures and robust security measures. Multimodal AI is transforming human-computer interaction, HCI, by integrating speech, facial expressions, and text input. Virtual assistants like Alexa, Google Assistant, and GPT-4v process multiple modalities for a seamless user experience. Beyond simple command recognition, multimodal AI enables emotion-aware computing, detecting sentiment from voice tone and facial expressions to enhance interactions in customer service, education, and mental health applications. However, ethical concerns arise regarding bias, user privacy, and deepfake misuse, requiring careful AI governance and transparency. Multimodal fusion strategies determine how information from different modalities is integrated. Early fusion combines raw features at the input stage, ensuring tight integration but increasing model complexity. Late fusion, in contrast, processes modalities independently before merging predictions, making it modular and interpretable, but sometimes less effective in learning cross-modal interactions. Intermediate fusion balances the two, dynamically learning interactions between modalities within the model, as seen in cross-attention transformers and graph neural networks, GNNs. Each strategy has trade-offs. Early fusion offers deep integration, but requires aligned multimodal data, while late fusion provides flexibility, but may lose fine-grained cross-modal relationships. Selecting an appropriate fusion strategy depends on the application, dataset characteristics, and computational constraints. Attention mechanisms are essential for multimodal learning. Self-attention allows a modality to attend to its own features, while cross-attention enables different modalities to interact, improving representation learning. Cross-attention is widely used in vision language models like Flamingo and Blip, where text and image embeddings are jointly processed to generate meaningful outputs. Query key-value interactions in transformers ensure that relevant features from each modality are emphasized, reducing noise and improving model accuracy. One challenge is interpretability, understanding which features contribute to a model's decision-making. Techniques like attention visualization and probing methods help researchers analyze cross-modal dependencies, ensuring better model transparency and trustworthiness. Few-shot and zero-shot learning enable multimodal models to generalize to unseen data with minimal supervision. Pre-trained models like CLIP use contrastive learning to align images and text, enabling zero-shot classification without direct supervision. This has vast applications, including image search, captioning, and text-to-video retrieval. Few-shot learning leverages prompt tuning and adapters to fine-tune models on small datasets. However, challenges include handling novel modalities, ensuring consistent alignment across modalities, and mitigating domain shift issues. Advances in meta-learning, retrieval-augmented learning, and parameter-efficient tuning are helping bridge these gaps, making multimodal AI more flexible across domains. Large language models, LLMs, are evolving to support multimodal inputs, bridging the gap between text and perception-based intelligence. Models like GPT-4v, Gemini, and Cosmos incorporate vision and text understanding, enabling image captioning, reasoning over documents with images, and visual question answering, VQA. Challenges include grounding textual descriptions with real-world perception, as language models may lack deep spatial and common-sense understanding. Research in multimodal chain-of-thought reasoning, reinforcement learning with human feedback, RLHF, and retrieval-augmented generation, RG, is pushing toward more context-aware multimodal AI. The future of LLMs involves better spatial temporal reasoning, handling dynamic video-based tasks, and integrating audio for richer interactions. Multimodal AI requires effective knowledge representation to encode diverse data types in a common framework. Embedding-based approaches map different modalities, e.g., text, images, and audio, into a shared latent space, enabling seamless cross-modal retrieval and reasoning. Beyond embeddings, graph-based representations integrate structured knowledge, such as semantic relationships in knowledge graphs, e.g., ConceptNet, Wikidata. Neural symbolic approaches combine deep learning with logical reasoning, allowing models to leverage explicit world knowledge alongside learned representations. However, aligning structured, e.g., knowledge graphs, and unstructured data, e.g., images, text, remains a challenge. Advances in self-supervised multimodal graph learning and contrastive knowledge alignment are improving representation learning for multimodal AI. Data diversity is crucial for robust multimodal AI. Augmenting multimodal datasets involves modality-specific transformations such as image cropping, text paraphrasing, and audio pitch shifting to enhance generalization. Generative models like GNs, diffusion models, and multimodal VEs create synthetic data, filling gaps in underrepresented categories. For instance, text-to-image models, e.g., DAL, Stable Diffusion, generate diverse visual representations for training vision language models. However, challenges include domain adaptation, e.g., synthetic images may not match real-world distributions, and bias amplification if training data lacks diversity. Strategies like domain adversarial training, data mixing techniques, and fairness-aware augmentation help mitigate these issues. Self-supervised learning, SSL, enables models to learn multimodal representations without extensive labeled data, making it scalable across domains. Popular SSL approaches include contrastive learning, e.g., CLIP, aligns modalities by maximizing similarity between paired data, text-image, while minimizing unrelated pairs. Masked modeling, e.g., ME for images, BERT for text, learns representations by predicting missing parts of the input, improving robustness. These methods enhance generalization, domain transfer, and sample efficiency, making multimodal AI more effective in low data settings. However, SSL models require large-scale pre-training and careful design of positive/negative pairs to prevent learning spurious correlations. Multimodal AI is increasingly being personalized to adapt to individual user preferences. Applications include personalized recommendation systems, e.g., Netflix, YouTube, combining viewing history, text, thumbnails, images, and audio analysis. Adaptive learning platforms adjusting teaching materials based on multimodal interactions, e.g., speech, handwriting, gaze tracking. Reinforcement learning-based adaptation, where AI systems dynamically adjust responses based on user feedback. However, challenges remain in preserving user privacy, mitigating biases in personalization, and ensuring fairness across demographic groups. Federated learning and differential privacy techniques help enable personalization without exposing sensitive multimodal data. Explainability is essential for ensuring that multimodal AI systems make interpretable and trustworthy decisions. Because these models integrate multiple data sources, it can be difficult to determine how different modalities contribute to predictions. Challenges include understanding interactions between modalities, high-dimensional feature representations, and ensuring explainability without sacrificing accuracy. Popular techniques include attention maps, e.g., GradCM, to visualize important regions in images or text. Feature attribution methods, e.g., SHAP, LIME, to estimate the impact of each input feature. Counterfactual reasoning to test how model outputs change when specific inputs are modified. While improving explainability, these methods often come with trade-offs in computational efficiency and may not fully capture how deep networks process multimodal data. Addressing these challenges remains a key research focus. Multimodal models often face domain shifts, where the distribution of data changes between training and deployment. For example, a model trained on high-quality medical scans may struggle with scans from different hospitals. Challenges include aligning different modalities under shifting conditions, ensuring robust generalization, and handling missing or noisy data. Key techniques include adversarial domain adaptation, where a domain discriminator helps models align feature spaces across domains. Self-supervised adaptation, where models learn transferable representations using contrastive learning or masked pre-training. Cross-lingual adaptation, where text-based models generalize to unseen languages by leveraging multimodal embeddings. These techniques improve multimodal AI's ability to function in diverse real-world settings. Reinforcement learning, RL, enables multimodal models to learn from interactions rather than static datasets. In multimodal AI, RL can be used to optimize decision-making in robotics, dialogue systems, and recommendation engines. Examples include robotics, where agents process vision, tactile, and audio inputs to navigate environments. Conversational AI, where RL fine-tunes responses using text, tone, and facial expressions. Multimodal recommender systems, which adjust recommendations based on user interactions across different content formats. Challenges include balancing multiple reward signals, ensuring stability in training, and handling high-dimensional multimodal inputs efficiently. Future research focuses on multi-agent RL and self-supervised reward functions for better generalization. Self-supervised learning, SSL, enables multimodal AI to learn representations without relying on labeled data. This is especially useful when obtaining labeled multimodal datasets is expensive or impractical. Key SSL approaches include contrastive learning, e.g., CLIP, trains models to align image-text pairs by bringing relevant embeddings closer. Masked modeling, e.g., data2vec, learns to predict missing modalities, similar to how BERT masks words and text. Notable models like Forens integrate SSL for large-scale multimodal learning, improving generalization, transfer learning, and robustness. SSL helps AI systems learn from vast unstructured data, reducing reliance on manual labeling and enhancing scalability. Cross-modal retrieval allows AI to search and align content across different data types, such as retrieving images using text queries or finding relevant videos from audio descriptions. Key techniques include shared embedding spaces, where different modalities are mapped into a common vector space, e.g., CLIP for image-text retrieval. Cross-attention mechanisms, where models attend to relevant features across different inputs to improve search relevance. Applications include multimodal search engines, e.g., Google Lens, multimodal question answering. Media retrieval, where AI retrieves video clips based on spoken or textual descriptions. Security and surveillance, identifying objects or people across video, audio, and sensor data. Challenges include ensuring scalability in large datasets and improving semantic alignment between different modalities for more accurate retrieval. Personalization in multimodal AI involves adapting models to individual user behaviors and preferences, leveraging inputs from multiple modalities such as text, images, and behavioral data. Examples include recommendation systems that combine viewing history, text, facial expressions, vision, and voice preferences, audio, to suggest content. Virtual assistants that personalize responses based on past interactions across text and speech. Healthcare applications, where AI tailors treatment plans based on medical images, patient history, and wearable sensor data. However, personalization raises ethical concerns. Privacy risks as multimodal systems process sensitive user data. Algorithmic bias, where models might favor certain demographics based on biased training data. Ensuring fairness and transparency in personalized multimodal AI remains an ongoing research challenge. Robustness in multimodal AI ensures that models generalize well across different domains and handle real-world variability. Since multimodal systems integrate diverse data sources, they are more susceptible to noise, missing data, and adversarial attacks. Key techniques for improving robustness include adversarial training, where models learn to resist perturbations in input modalities. Data augmentation, generating synthetic variations of multimodal inputs to improve generalization. Domain adaptation, adjusting models to perform well in new environments using transfer learning and fine-tuning. Evaluating robustness involves out-of-distribution, OD, testing, where models are assessed on previously unseen data distributions to ensure reliability. Multimodal AI introduces new ethical challenges due to its ability to process and combine data from multiple sources, potentially leading to biases, privacy issues, and lack of transparency. Key concerns include bias in multimodal datasets. Models may inherit biases from unbalanced training data, leading to discrimination in facial recognition, speech processing, or healthcare AI. Privacy risks. Multimodal AI collects data from text, images, voice, and sensor inputs, raising concerns about user tracking and surveillance. Transparency and explainability. Deep learning models, particularly transformers in multimodal AI, often lack interpretability, making it hard to justify decisions in critical applications like medicine and law. Mitigation strategies include bias auditing and fairness-aware training to reduce discrimination in multimodal predictions. Privacy-preserving learning methods such as federated learning and differential privacy to protect user data. Explainable AI, XAI, techniques that make multimodal AI decisions more interpretable, such as attention visualizations and saliency maps. The future of multimodal learning is rapidly evolving with several groundbreaking advancements. Generative multimodal models. Models like GPT-4V and DALL-E enable AI to generate text, images, and even videos from multimodal inputs. This trend is transforming creative industries, content generation, and interactive AI applications. Self-supervised and few-shot learning. Future multimodal systems aim to learn from limited data using self-supervised pre-training and few-shot adaptation. This will enhance data efficiency and adaptability to new environments. Multimodal AI in AR/VR. The metaverse, gaming, and immersive training applications will increasingly rely on real-time multimodal fusion of speech, gestures, and environmental data. AI-driven multimodal interfaces will enhance human-computer interaction in mixed reality settings. Towards artificial general intelligence, AGI. Multimodal learning is a crucial step toward AGI, allowing models to process and reason across diverse information sources like humans do. Multimodal AI is expected to redefine how machines interact with the world, creating more intelligent, context-aware, and adaptive systems. Reinforcement learning, RL, is a machine learning paradigm where an agent learns by interacting with an environment to maximize a reward signal. Unlike supervised learning, where models learn from labeled data, or unsupervised learning, which focuses on finding patterns, RL is based on trial and error learning. Key components of RL include agent, the decision-making entity; environment, the world in which the agent operates; state, the agent's current situation; actions, choices available to the agent; reward, a numerical signal indicating success or failure. RL has been successfully applied in robotics, game playing, AlphaGo, OpenAI 5, self-driving cars, recommendation systems, and finance. However, RL suffers from issues like sample inefficiency, instability, and the high cost of trial and error learning in real-world scenarios. Recent advancements in deep reinforcement learning, DRL, meta-learning, and model-based RL have improved its applicability and efficiency. Reinforcement learning operates in an interactive loop between an agent and its environment. The agent observes a state, takes an action, and receives a reward, influencing future decision-making. Key elements. Policy. Pi defines the agent's behavior by mapping states to actions. Value function. V measures the expected cumulative reward of a state. Q function, Q, S, A, estimates the expected return of taking action in state S. Model of the environment. Optional predicts next states and rewards. A fundamental challenge in RL is the exploration-exploitation trade-off. Exploration allows discovering new, potentially better strategies. Exploitation leverages known strategies for immediate rewards. Balancing both is crucial for efficient learning. Techniques like epsilon-greedy, upper confidence bound, UCB, and Thompson sampling help manage this trade-off. Reinforcement learning problems are often modeled as a Markov decision process, NDP, which provides a mathematical framework for decision-making under uncertainty. An MDP is defined by states, S representing all possible situations of the agent; actions, A the choices available in each state; transition function, PSS, A the probability of moving from state S to S after taking action A; reward function, RSA, defines the immediate reward received after taking an action in a state. Discount factor, gamma, determines the importance of future rewards. A value close to 1 prioritizes long-term rewards, while a lower gamma favors short-term gains. MDPs are Markovian, meaning that the next state only depends on the current state and action, not past history. Solving MDPs involves finding the optimal policy that maximizes the expected cumulative reward. A policy, pi, defines the agent's strategy for selecting actions in a given state. Policies can be deterministic, pi s equals A always selecting the same action for a given state S; stochastic, pi as, assigning probabilities to actions, ensuring exploration. The goal of RL is to find an optimal policy, pi asterisk, that maximizes cumulative reward. This is measured by the expected return, which depends on finite horizon setting, considering a fixed number of steps; infinite horizon setting, using a discount factor, gamma, to weigh future rewards. Two key approaches to policy optimization: value-based methods, e.g., Q-learning learn an action value function and derive a policy from it; Policy-based methods, e.g., policy gradient, directly optimize policies using gradient-based techniques. The policy improvement theorem ensures that iterative refinements lead to better strategies, forming the foundation of policy iteration algorithms. Value functions estimate the expected return from a state or state action pair. State value function, vpi s, measures the expected return starting from state s under policy pi. Action value function, qpi s a, estimates the expected return if the agent takes action in state s and follows policy pi thereafter. The Bellman equation provides a recursive decomposition of value functions, forming the basis for algorithms like dynamic programming, DP, Q-learning, and deep Q networks, DQN. The optimal value function Q, S, A, asterisk leads directly to the optimal policy pi star. The Bellman equation expresses the value of a state in terms of its successor states. For optimal policies, we use the Bellman optimality equation. This recursive formulation allows us to compute value functions iteratively. Two main approaches in dynamic programming, DP. Policy evaluation, iteratively estimate vpi, S, for a given policy. Policy iteration, improve policies based on updated value functions. Challenges in applying DP to RL, requires a known environment model, not always available. Computationally expensive for large state action spaces, often replaced by model-free RL techniques like Q-learning and policy gradients. Reinforcement learning methods are classified into model-free and model-based approaches. Model-free RL, no assumption about the environment's transition dynamics. Value-based, e.g., Q-learning, and policy-based, e.g., policy gradient, methods fall into this category. Requires a large number of interactions with the environment. Model-based RL tries to learn the environment's transition model, PSSA, enables planning and sample-efficient learning. Examples, DynaQ, integrates planning and learning, model-based DDPG for continuous control tasks. Trade-offs. Model-free methods are simpler but often inefficient. Model-based methods are more efficient but harder to design and train. Hybrid approaches, e.g., AlphaZero, combine both strategies for improved performance. Q-learning is a fundamental value-based RL algorithm that aims to learn the optimal Q values for state action pairs. It follows the Bellman equation to iteratively update Q values. Key aspects of Q-learning. Uses temporal difference TD learning, updating Q values before the episode ends. Off-policy algorithm. The agent updates Q values using max Q, S, independent of its current policy. Guaranteed convergence under certain conditions, sufficient exploration, decreasing learning rate. Q-learning struggles with high-dimensional state spaces, leading to the development of deep Q networks, DQN, which use neural networks to approximate Q values. Deep Q networks, DQN, address the scalability limitations of traditional Q-learning by using neural networks to approximate Q values. Key innovations. Experience replay stores past experiences, SARS, in a buffer and samples randomly to break correlation and updates. Target networks maintains a separate target Q network, Q, to stabilize updates by periodically copying weights. Deep CNNs as feature extractors, used in Atari 2600 games, Breakout, Pong, Space Invaders, to handle pixel inputs. DQN achieved superhuman performance in many Atari games, demonstrating the potential of deep reinforcement learning. However, it still struggles with sample inefficiency, overestimation bias, and stability issues, leading to improvements like double DQN, dueling DQN, and rainbow DQN. Introduction. Q-learning is one of the most famous model-free reinforcement learning algorithms. The goal is to learn a policy that maximizes the total cumulative reward over time. Key concepts. Q value, quality, the expected return, reward, of taking an action. I in state S and following the policy thereafter. Action value function Q, S, A represents the expected cumulative reward for taking action from state. And following the optimal policy thereafter. Q-learning update rule. The algorithm uses the Bellman equation to update the Q values. In reinforcement learning, exploration allows an agent to discover better strategies, while exploitation maximizes rewards based on past experiences. A fully greedy policy always picks the best known action, but this can trap the agent in a local optimum. Conversely, excessive exploration slows down learning. A widely used method to balance this is epsilon-greedy exploration. Initially, the agent takes random actions frequently, high epsilon, but over time, it shifts to mostly choosing the best-known action, epsilon decay. This ensures the agent first explores the environment and then exploits its findings. Advanced approaches like upper confidence bound, UCB, prioritize actions with high uncertainty, while Thompson sampling uses a probabilistic model to decide exploration dynamically. These techniques help optimize learning, especially in non-stationary environments where the best action can change over time. SARSA is an on-policy reinforcement learning method, meaning it updates its Q-values based on the actual action chosen by the agent. Unlike Q-learning, which assumes the agent will always take the best possible future action, SARSA follows the policy it is actively using. This results in more stable learning, but slower convergence to the optimal policy. Since it doesn't assume an ideal future action, SARSA is better suited for environments with unpredictable rewards, where aggressive exploitation could lead to suboptimal performance. SARSA is particularly useful when an agent's policy includes exploration, as it learns from its real behavior rather than theoretical optimal moves. This makes it a good choice for safe reinforcement learning, where suboptimal actions should be avoided during training, e.g., in robotics or financial applications. Deep Q networks, DQN, extend Q-learning to large, complex environments by replacing traditional Q tables with a neural network. This is crucial for tasks like playing video games or robot control, where states are high-dimensional, e.g., raw pixel inputs. However, training deep networks directly on Q values leads to instability and divergence. To address this, DQN introduces two techniques. Experience replay stores past transitions and samples them randomly for training. This breaks correlation between consecutive updates and improves data efficiency. Target network uses a separate, slowly updated network for Q-value estimation, reducing fluctuations in learning. These improvements enable DQN to learn efficiently from raw sensory data, outperforming traditional reinforcement learning methods in complex, dynamic environments. Advantage Actor Critic, A2C, improves policy optimization by combining value-based and policy-based approaches. The actor, policy network, selects actions, while the critic, value network, evaluates how good the chosen action is. This separation makes learning more stable and efficient compared to simple policy gradient methods. A key improvement is the advantage function, which measures how much better, or worse, an action is compared to the expected value of the state. This reduces high variance in policy updates, leading to more reliable learning. A 2C is particularly useful for continuous action spaces, where Q-learning struggles. It has been applied in robotics, gaming, and financial decision-making, outperforming basic reinforcement learning techniques in complex, high-dimensional environments. Policy gradient methods take a direct approach to reinforcement learning by optimizing the policy itself rather than relying on value functions. This makes them well-suited for continuous or high-dimensional action spaces, such as robotic control. Unlike Q-learning, which selects actions based on estimated values, policy gradient methods learn stochastic policies, meaning they sample actions from a probability distribution. This improves exploration and allows the agent to escape local optima. However, these methods often suffer from high variance, making training unstable. Techniques like advantage estimation, used in A2C, and baseline subtraction help reduce this issue. Despite the challenges, policy gradient methods form the foundation of modern deep reinforcement learning, powering algorithms like PPO, proximal policy optimization, and TRPO, trust region policy optimization. Proximal policy optimization, PPO, is a popular reinforcement learning algorithm that improves policy gradient methods by ensuring more stable and reliable updates. One key innovation is its clipped objective function, which prevents updates that are too large, reducing instability in training. PPO also uses a method called trust region optimization, which keeps policy updates within a safe limit, preventing performance collapse. This balance between exploration and exploitation makes it one of the most widely used RL algorithms today. PPO has been successfully applied in robotics, where precision is crucial, and in autonomous systems like self-driving cars and drone navigation. It also powers AI in complex games, including OpenAI's Dota 2 agent and DeepMind's AlphaStar. Reinforcement learning has expanded beyond academic research into real-world applications. In robotics, RL enables robots to learn tasks like object manipulation and locomotion. In healthcare, it helps optimize treatment strategies, while in finance, it's used for algorithmic trading and risk management. One of RL's strengths is handling dynamic, uncertain environments, making it ideal for self-driving cars, industrial automation, and adaptive control systems. However, real-world deployment faces major challenges, including sample inefficiency. Training an RL agent requires massive amounts of data. Reward shaping. Defining the right rewards is difficult and can lead to unintended behaviors. Safety concerns. Unsupervised exploration can be risky in critical applications. To overcome these, researchers explore techniques like meta-learning, offline RL, and human-in-the-loop training, making RL more practical for real-world use. A major limitation of reinforcement learning is sample inefficiency. Many RL algorithms need millions of interactions to learn optimal behaviors. This is impractical for real-world applications like robotics and healthcare, where collecting data is costly. One approach to improving efficiency is model-based RL, where the agent learns a model of the environment and simulates interactions before taking real-world actions. This reduces the number of required real interactions while improving learning speed. Another promising approach is offline RL, which learns from previously collected datasets without interacting with the environment in real time. This is particularly useful for medical and financial applications, where unsafe exploration must be avoided. Many state-of-the-art methods combine model-free and model-based approaches, balancing efficiency and adaptability. Future advancements in transfer learning, meta-learning, and imitation learning will further reduce the data demands of RL. Reinforcement learning agents maximize rewards, but poorly defined reward functions can lead to unintended behaviors. This is known as reward hacking. For example, an RL agent trained to win a game might find a loophole instead of playing as expected. In high-risk applications like healthcare, finance, and self-driving cars, safety concerns are critical. RL agents may act unpredictably when faced with edge cases not covered in training. To mitigate risks, researchers implement human-in-the-loop learning, constrained RL, and robust evaluation techniques to ensure safe decision-making. Another concern is bias in RL systems. If trained on biased data, RL agents can reinforce unfair policies in areas like hiring, lending, or criminal justice. Addressing this requires techniques like fairness-aware RL and diversity-driven exploration. As RL continues to influence real-world applications, ensuring safety and ethical compliance will be essential to responsible AI deployment. Reinforcement learning is evolving rapidly with advancements in scalability, generalization, and real-world adaptability. Larger RL models trained on diverse data improve performance, but generalization remains a challenge. One major direction is integrating RL with unsupervised learning, enabling agents to learn representations without explicit rewards. This approach makes RL more adaptable across different tasks. Multi-agent RL is another key area where agents learn to collaborate or compete, useful in areas like autonomous systems, economics, and large-scale simulations. Bridging the gap between simulated and real-world RL is also crucial. Approaches like sim-to-real transfer, domain randomization, and human-in-the-loop training help RL systems become more robust and deployment-ready. Reinforcement learning has transformed robotics, allowing robots to learn manipulation, walking, and autonomous navigation. Instead of hard-coding rules, RL lets robots adapt through trial and error. One challenge is the sim-to-real gap. Models trained in simulation often fail in the real world. Techniques like domain randomization help RL models generalize better. To improve efficiency, researchers use hybrid RL methods, combining model-based RL with supervised learning. This makes learning faster, safer, and more sample efficient. Applications include robotic arms in factories, autonomous drones, and exoskeletons for medical rehabilitation. Self-driving cars use RL to optimize decision-making in dynamic environments. RL enables real-time adaptation for lane changing, merging, and obstacle avoidance. However, safety is a challenge. Exploring risky behaviors is dangerous. Safe RL techniques, including reward shaping and human feedback, help prevent unsafe actions. Most self-driving systems combine RL with rule-based methods, ensuring stability and reliability while allowing cars to learn from experience. The future of RL in self-driving includes multi-agent learning, handling multiple vehicles, and better simulation-to-reality transfer for training in virtual environments. Reinforcement learning is revolutionizing healthcare by optimizing treatment planning, robotic surgery, and drug discovery. For example, RL can personalize chemotherapy schedules based on patient responses. However, RL in healthcare faces data scarcity. Doctors cannot experiment freely. Offline RL, which learns from historical data without new interactions, is a solution. Ethical concerns include patient safety and fairness. RL policies must avoid bias and ensure equitable treatment recommendations. As RL advances, its integration with causal inference and human oversight will enhance trust and reliability in medical decision-making. Reinforcement learning is widely used in finance, particularly for algorithmic trading, portfolio optimization, and risk assessment. RL agents analyze market trends to make profitable decisions. However, markets are non-stationary and highly volatile, making RL models prone to overfitting. Techniques like adaptive learning and uncertainty estimation improve robustness. Human traders often work alongside RL systems to override extreme decisions. Future advancements include multi-agent RL for market simulations and deep RL for more complex trading environments. Reinforcement learning has made breakthroughs in game AI, achieving superhuman performance in games like Go, AlphaGo, Poker, Deep Stack, and StarCraft II, AlphaStar. Game RL models often use multi-agent learning, where agents compete or collaborate to refine strategies. Self-play, a technique where the agent plays against itself, accelerates learning. However, RL in games often overfits to specific environments. Models that excel in one game fail in others. Future research focuses on generalizable RL models that transfer knowledge across tasks. Industries use RL to optimize processes, reduce waste, and automate tasks. For example, RL helps manage supply chains by predicting demand and optimizing inventory. Energy companies use RL to reduce consumption, optimizing power grids and HVAC systems. Robotic automation in factories also benefits from RL-driven scheduling. Simulated environments allow RL models to train safely before deployment, making industrial RL practical for real-world use. Multi-agent RL, MARL, extends RL to environments where multiple agents interact. Applications include autonomous vehicle coordination, swarm robotics, and multiplayer strategy games. Agents can learn to cooperate, e.g., robotic teams, or compete, e.g., financial markets. A key challenge is scalability. As the number of agents increases, learning stability declines. MARL research focuses on communication learning, where agents exchange information to improve collaboration. Future improvements will enable MARL in smart cities, defense systems, and logistics. MetaRL, or learning to learn, allows agents to generalize across tasks instead of starting from scratch each time. This is crucial for real-world AI, where environments constantly change. Techniques like few-shot learning enable agents to adapt quickly with minimal data. Memory-based methods, e.g. LSTMs, and model-based RL improve transferability. MetaRL is essential for robotics, autonomous systems, and AI assistance, pushing RL toward true general intelligence. Despite advancements, reinforcement learning still faces significant challenges that hinder its real-world adoption. One of the biggest issues is sample inefficiency. Most RL algorithms require millions of interactions to converge to optimal behavior. This is impractical for applications like robotics, where collecting real-world data is costly and time-consuming. Another challenge is generalization. RL models often overfit to the specific environment they are trained in and struggle to perform well in new, unseen scenarios. Unlike humans, who can apply knowledge flexibly, RL agents typically require retraining when faced with slightly different tasks. Meta-learning and transfer learning are being explored to address this limitation. Safety concerns are also critical, particularly in healthcare, self-driving cars, and finance, where an RL agent making an unsafe decision can have severe consequences. Ensuring safe exploration and incorporating human oversight into RL training remains an ongoing research area. Finally, computational costs are a bottleneck. Training large-scale RL models, especially deep RL architectures, requires enormous compute power and time. Techniques like distributed RL, pruning, and model compression are being developed to make RL more efficient and scalable. Addressing these challenges will be key to making RL more widely applicable in real-world industries. Reinforcement learning has transformed AI research and applications, demonstrating its power in areas like robotics, gaming, finance, and autonomous systems. From AlphaGo's victory over human champions to self-driving cars optimizing decisions, RL continues to push AI's boundaries. However, the future of RL will likely involve hybrid approaches, combining RL with unsupervised learning, imitation learning, and symbolic reasoning to improve generalization and stability. The integration of neuroscience-inspired learning techniques may also help RL agents mimic human cognition more effectively. A key development will be human-in-the-loop RL, where human guidance helps shape agent behavior. This approach will be vital for safety-critical applications, ensuring RL agents do not make dangerous or unethical decisions. Explainability and interpretability of RL models will also be crucial in fostering trust and accountability. Finally, scalability remains a major challenge. To make RL practical for real-world decision-making, researchers are exploring more efficient training techniques, transfer learning, and better hardware acceleration. By overcoming these hurdles, RL has the potential to revolutionize multiple industries and pave the way for more autonomous, intelligent, and adaptable AI systems. Thanks for watching. This concludes our Day 6. For more AI courses and interview materials, please go to our website at bowz8.com.